working on the logic for this HATS system, or this stable chaos model, and there's this relationship here between these nodes or potential nodes. Let's go ahead and copy these. Okay, so basically there's this model that A is like AB, and then B is like AB, but A and B are not like one another. AB and not A, not B are also not like one another, but they share a likeness in the fact that A is like not B and B is like not A. And so there's this constant. If we took out all of these states and we define them by potential states, there's this dynamic here where there's this relationship of likeness and dislikeness. And so what we're doing here is, if we program this out, we have this logic that says if we're looking at ourselves, we exit. If we're looking at our opposite, we repel it. And then we needed other rules for our left and right neighbors. In this case, we can only ever go up or down by 1, but we need to add a gradient here because there are infinite numbers between 0 and 1, and we should also scale incrementally. But for right now, we're just doing plus and minus 1 just to build this model. We're also using this little bit of randomness. Would be considered pseudo-randomness, but we're not getting into that. And actually, I'm not using real pseudo-random number generator. So we're just allowing Python to use its default random number, and then we use these to determine if we want to go up or down, also based on these relationships with our neighbors. And so the concept is, if we are like our left neighbor, we want to show more preference to a positive likeness to the A set, and if we are looking at our right neighbor, we want to show more of a likeness to our B set. This creates an interesting dynamic because the first node in the system here is always going to try to repel its opposite, and you would intuitively think that this is what creates the chaos here, but this is actually what creates the stability. It's in the attempting to be like its neighbor that the system continually creates chaos. So if this system is trying to be like both of these systems, and both of these systems are trying to be opposite of one another, there's always going to be this little bit of static or distortion. And in the fact that this is also trying to be invertedly like these, and these two are inverting each other, then this actually is what creates the stability in this system. But there is a little bit of cool refactoring we can do here. I was still working through the logic, and one piece of interesting information is, like, if both A and B, the random numbers, are greater than 1, then we want to move up. And if both A and B are below 0, then we want to move down. But only in the sense that if there's space to move down or space to move up. And so in this context, we don't care if it's a left or right neighbor, as long as it's not our opposite. So what we can do here is we can actually just return, and then we can move this piece of code out, because this stays the same regardless. So if we have an opportunity to overtake one of our neighbors, that's what we want to do, as if they're moving up and we're moving down. So we can do this regardless. And so if both of them are above 0, there will be no other option, so we will just return. So if our neighbors, both A and B states, are already 1, then we cannot move up. We cannot be exactly like our neighbor. We can only be like our neighbor. We cannot be the same as our neighbor. So that's where this rule comes in, and then we can move all this back, and so we can say if A is greater than 0, if our neighbor's A is less than 1, then we want to try to become 1. If their B is greater than -1, we want to also try to do the opposite of what they're doing in their other state. And then if they're the right neighbor, we want to inverse this logic. This was the same logic we just pasted up above, so now we can say, if we have zeros, we want to maintain our current state. That's right. So we can actually set an exit early condition here. If self.random, say, and there we go, boom. Obviously, I'm using Copilot. I like it for menial stuff like that, where logic kind of fits in itself. Problem with this model is we could potentially have more than one operation. Yeah, so we're refactoring that now, so that won't ever happen. So let's copy this because I know that this is full. If we're under the threshold, we want to inverse. Yeah, that's right. I'm not gonna. If I mix positive and negative, we want it to be like our neighbor in one way or another. So if, and there's actually a lot better way to do this. This is very simple code. There's a lot more sophisticated ways that I could refactor this and use inline ternary assignments, and that's not always good. But in this case, you have positive and negative values. You could actually just attribute those to these values based on the state of this. There's bitwise operations and so many other things that you could do. But what we want to do is the opposite here. So if A is less than 1, we want to try to be like it in that way. And if B is less than negative 1, we actually want to try to do the opposite. We want to go the opposite direction. If it's, we want to try to overtake B. And really what we need to do is change the logic here too. So if it's greater than negative 1, and if B is less than 1. So we want to invert our logic. That's essentially all we do. And it's really almost the same logic here, actually, now that I think about it. So we could even simplify this more. Because we have 4 minus A conditions. So we have 3 minus A, 3 add B. Oh, something's not right here, is it? Oh, because we weren't done here. So I almost feel like we're doing the same thing. The over 1 less than 0. Okay, so greater than negative 1. I'm confusing myself. Okay, let's just swap these. Greater than negative 1, less than 1. Greater than 0, greater than, can't be greater than 1, greater than 0. No, we want to leave those. This level of logic doesn't change, this level does. So if it's less than 1, or if it's greater than negative 1, if it's greater than negative 1, or less than 1, and then if it's less than 1 and greater than negative 1. So we can actually flip this state too, because we see this in multiple places. So, and there's a lot of ways you could represent the same logic. See right here, the difference is that we're going to minus an A versus add an A, so we can't combine these. And also the condition here, we could combine somewhat of this, but this is very simple. We're not going to change this. So part of this isn't right. So let's think about this. If our left neighbor, we want to show a preference towards A. So if A is less than 1, then we want to minus it. Minus A. If node D is greater than negative 1, so if it's higher, we want to do the opposite of it. We want to minus B. we need to continue this logic all the way through this side, because we're deciding what we do based on our own randomness, and then attributing that randomness to the likeness of our neighbor. And this is probably above some people's heads and beyond what some people are interested in, and that's fine. This is not meant for everyone. Some people would call this theoretical quantum physics, quantum mechanics, or things like that, and I don't really know what this is, but so if A is greater than -1, if random A is less than -1, so that's if we want to make a move down. We should also be checking our A state, but we're doing that internal to this, so if it's greater than -1, I feel like we should be checking if it's greater than 0. If it's greater than -1, we want minus A. If it's less than 1, we want minus A. So let's look at it like this. We're going to say that if random A is a positive, we want to do like our left neighbor in the A direction. So if A is less than 1, we want to minus A. We don't want to overtake it. And if B is greater than -1, we want minus B because we do want to overtake it. So if random A is less than 0, which means we want to do the opposite. If our A is greater than -1, we want to add A because we don't want to overtake it. But if B is less than 1, we want to add B because we do want to overtake it. So this logic, you can see clear logic here now. So in B, if random B is a positive, we want to do the opposite. So our left neighbor, we want to try to do the opposite of B no matter what. So we don't have to check B. We already have calculated B here based on what we're doing with A. So our A logic decides what we do on the B side. Yeah, and that attributes A and B to the association of our neighbors. And this will be uniform throughout all of our nodes. So we can get rid of random A here, and we say if random B is, and this is cool because if they're both positive or both negative, we disregard whether they're left or right. So there's some chaos introduced here, but it's going to try to self-stabilize, and it's always going to stabilize because of our opposite. So we're always going to try to do the opposite, and again, that's going to give us a deterministic factor, and this should give us some emergent behaviors, or what would appear. So if it's the right neighbor, if it's random, B is a positive, is B positive, we want to do like our right neighbor in B direction. And we could also combine these logics as well, but I think this is the simplest way. We don't need, cannot be left and right neighbor. So if we get to this point, we're just going to return, and we'll do the same thing here. So if random B is greater than 1, and random B is, let's see, how do we do this? Greater than -1, we want to add B. If it's less than 1, we want to try to overtake it. We want to add A. If it's less than 1, to the opposite. So if b is less than 1, we want, ooh, what do we also want to add? It's a little confusing when I think about it like that. Oh yeah, we don't want to overtake it. We want a minus b so that we do not overtake our neighbor's b. And then also we want a minus b minus a. Yeah, okay. So if we decide to make a positive move here, if it's this neighbor, we want to see, because this is why this works. So we only calculate randomness once, and then we iterate through all of our neighbors. So we're going to try to stabilize against our opposite. We're going to try to be like our left neighbor in the A, and be like our right neighbor in the B, and then also try to do the opposite of those neighbors in the opposite fields. So there's going to be this like a little bit of chaos here. So return C on node. Where did I do that? 134. Let's make sure this is right. So our right neighbor for A would be B, our right neighbor would be for A. Okay. These are very simple portions, and we could simplify that even more, but let's see. And this is pretty slow. This one has less chaos in it than it did before. I'm curious if it seems to self-stabilize. I think there's a problem in our opposite node. No, in our repel state. So since we changed the logic in the other states, repel if node A is greater if node A is greater than 0, we want a minus 1, else if node A is less than 0, we want to add 1, and then we'll do the opposite here. And there's a lot better way to program this, but I'm not going to worry about that right now. Yeah, there we go. You can see this thing tries to stabilize, but we're also, I think, doing coloring wrong. Let's see, if A and B are greater than 0, we need to be doing our white fill. And if A and B are less than 0, we need to do our black fill. And then we need to add one more thing to our state. So if node A equals 1 and node B equals 1, then we want to say self A equals -1. We don't use those in Python. So if we reach an absolute state, we automatically want to toggle the inversion. Oh, color does not have a black fill. And so this is where we should actually be using gradients, because there's a lot more states than just 0 or 1. There's this interesting thing here where we should not be seeing these opposites like this. So we need to check our logic for this level. But you can see here, I mean, this model could be expanded further. It tries has to self-stabilize, but it's always in this constant state of chaos or flux. There are obviously bugs in this code. Some appear to be more random than other. And then if we expand it even more, because right now we're running our engine at 10 frames a second just to make it slow enough to see. If we ran this thing at full regular capacity, you would see this thing like moving in and out of states fast enough to where you can see stable state change and shift, but you also see this modularity or recurrence. So that's why I call this a hybrid abstract transitory structure, or simply a stable chaos model. And to go further ado, this is running at 60 frames a second through my CPU. If we were to attach this to my GPU and run it at like 5 gigahertz, or attach it to a quantum computer where we run at the speed of light, I don't know what this would look like. And then also further, these are individual components of a single system, so we could essentially create arrows or maps here showing how these things are relating to their neighbors. We could add metrics to count the number of shift changes and number of iterations for visiting certain states. We could lerp between these points, and beyond that, we could also add a summation of the entire state of the system and see the collective state change, and then scale this thing to, say, 10,000 nodes. But yeah, I'd be interested in hearing anybody's thoughts. I'm very interested in what people think this could be useful for, or feedback on how the system could work or may even be useless. But yeah, you can check out the code on GitHub. You can shoot me a like, subscribe,